Good morning. Just when I thought I could get out, they pulled me back in. So this is John Jones again. I haven't seen y'all for about 3 sessions because they need to get the smart guys to come in here and do the talking. So now when it's basic meter math, they figured I could handle that, so they asked me to do this one and then the one Thursday as well. So I'm glad to be back here in the bunker again with Jarrett and Chris. So just wanted to go over the list of things we always talk about here at the beginning, which is, of course, we've got today we're going to do basic meter math. Then Thursday we've got intro to meter testing. I'll be doing that one, and then they're going to bring back in the smart folks again to do the 4 quadrant metering and the ANSI C12 updates. So what are we going to talk about today? So we're going to talk about the basic meter math, which is we're going to talk about that math is used for basic power and energy calculations. Algebra, that we use that a little bit to try and find some unknown quantities that we can use sometimes out in the field. And then trigonometry is used for some of these vector calculations because you know how important vectors are to us out there in the field. So what I've thought about this class, and there are some other courses and classes out there. They got some great courses, and there's curriculums have been set up, like Who's Your Energy and Electric Cities, people like that. They've come up with some some serious curriculums on this. So they'll spend several classes and sessions on this math. But we're just going to hit it here in this one session. So I'm going to keep it basic. But on top of that, I want to apply it more to what is in the field. So I'm going to take breaks in what I'm talking about when we talk about either values or calculations or these vectors, and stop for a minute and say, but how does that apply to me when I'm standing at the pole? How does that apply to me when I'm looking at my piece of equipment? Okay, it's similar to, you read in the Bible and then but how can I apply that to my daily life? And of course, I'm using that as a lead-in because, always pray before we get rolling. And I guess looking at the news, I can't think of a better time to pray than now. As a matter of fact, Jarrett made a great, I saw a stat that said, almost half of the people in this country that don't even, would categorize themselves as Christians are praying right now, because between the V's of violence and virus right now, it's kind of crazy in this country right now, isn't it? So the comment was made, I can't believe those many people that don't believe are praying. And Jarrett made the comment, which was very true. He said, well, is there really they said, well, how would they know how to pray? And Jarrett said, well, is there really a bad way to pray? And that's true. So that's what we're going to do to start out this morning. We're going to pray for this country and pray for what's going on, because, it's pretty disturbing to even have to look at the news these days. It's very upsetting, and some of it I have a hard time stomaching, especially the initial incident. It was just horrific. So I'm going to go ahead and open up with a prayer real quick, and then we'll get rolling. Precious Heavenly Father, right now our country's in turmoil on a lot of different fronts. So we've got a pandemic, we've got riots around the country, and just all this crazy infighting with politicians when they should be concentrating on just getting us whole again. And so, Father, we just lift the country up to you and ask that you would put your hand on us, keep your hand on us, and just let people have more of an open mind, and let people just try and be fair and honest with themselves. This is always a heart issue, Lord. It's a heart of each and every one of us out there. And let us not take things and twist them into something else, but we have to be responsible for our own hearts and our own actions. And we see some horrible things going out there, Lord, and we just lift this country up to you and lift what's going on up to you, and just ask that you can step in and help us, because it seems like it's spinning out of control. And Father, we know in your Bible you say that you put principalities and governments in place. And so, Father, it's hard to see it at times, but you're in control of everything. So please be with us and watch over us, and watch all these folks out there. They're out there working. It's starting to get pretty hot out there. We've got a lot of our people that work with us, our friends. They're part of the Powermetrix family and in our industry that are going to get out in this heat and stuff now, and they're working. And watch for them, because it's all about getting home to your family safe at the end of the day, Lord. So all of these things I ask and say according to the will of the one who paid it all, my brother, Jesus Christ. Amen. Thank y'all. All right. Well, let's get started. So I think the best way to get started on this, we've talked about this a little bit, is let's just talk basic, that's like I said. So we're going to just talk the relationship. It's one of the basic laws that we all talk about, Ohm's law. So we talk about, the relationship of voltage, resistance, and current. And you've heard me use it before, and I'll mention it here again later. This is actually the basis for one of the tests we run with our 3 series piece of equipment. So it's V equals IR. So if you go to the next one. So here you can see we're talking about the algebra here. If you were trying to find, if you wanted to just find resistance out of that equation, you can see what you would do here to find your resistance. And you remember we've talked about that previously when we talked about a piece of our equipment that does a certain test. That's what we were looking for, was the resistance. So that's once we knew the voltage, you've heard me say that, once we knew the voltage and once we knew the current, we were able to calculate the resistance. And that's what this is all about. So, but now one part about this is that, and I'm gonna write up here for just a second. You know me and whiteboards. And if I've ever been to your utility, you know I love to grab a whiteboard. So if we're talking about this, what we're talking about is, you have inversely proportionate and directly proportional, And if you see something that is directly proportional, as one increases, the other increases. As you make more money, you pay more taxes. Okay, so as you just go, that's two values are proportional with one another. In this case, when we're talking about our current and our resistance there, they're inversely proportional, in that when one goes up, the other comes down. And if you think about it, I'm just going to use a number. Remember we said V equals IR. Let me know if I need to get out of the way, boys. So if we got 100 volts here, which equals 10 amps times 10 ohms, so I get my 100 volts, right? Well, if the voltage stays the same, and let's say out there in the field, I have a drop in my current. So if my current drops to only 5 amps, okay, but remember, my voltage is staying at 100, what has to happen to my resistance? My resistance is going up, right, for this to still work. So this would have to go to 20 ohms. So when and we've seen this, we know we've seen the picture, and we know how that goes on the picture. If your resistance goes up, your current comes down, okay? So you remember on the picture that we saw just right before this, you can see it's choking it in that the ohms up there, the resistance, dude in the hat. So as he's choking it down, you get less flow of the amps or current through there. So that's exactly what happened on our equation too. As my resistance or my ohms goes up, my flow of current comes down. We a lot of times use the flow of water in a pipe about electricity. So here you can see that resistance or an increase in the resistance there chokes my pipe, and I don't get as much flow through it, okay? The voltage is still trying to drive it, but you can see here that my ohms right here are choking it off, okay? So we use that V equals IR as our base, one of our basic equations that we use, okay? And what is it that you and I are dealing with out there? We're talking about power, right? That's what we deal with, is power. So we're dealing with power right here. You've got, you can see here we've got the power law for DC, okay? So which that's just standard. Back when we were just dealing with only DC and we didn't have AC to deal with, you can see it was really easy. It was power just equals my volts time, it's the voltage times the current right there. So I got volts times amps gives me my just straight up watts on DC. But then for what you and I deal with, which is AC power, now we have those angles are thrown in there, right? We're starting to talk offsets of angles, and the dreaded power factor gets involved. So you can see here, it says that my power now equals my voltage times my current times my power factor. And the power factor is going to be this cosine of theta. So I'm going to go to the board again here for a second and kind of draw this, which is, we talked about the angles. We've talked about this before between my current and my voltage. If this was my heavy voltage, we're going to go over this again in a second. That the sign that they're talking about here, this cosine of theta, this is what's theta right here, okay? So that's what the power factor is. It's the cosine of theta, which for you and I on our equipment is always going to be between my current and my voltage vector. It's going to be that angle on the same phase. Okay, so both of these have got to be on the same phase, okay? We're going to go into that a little bit more here in just a second. So here's where we can look at it. We just talked about the V equals IR. Well, let's go ahead and apply that. So we can see here that you've got with a cosine, the cosine of theta, if I have unity, which I don't take anything away from it, and unity equals 1 for a power factor, it doesn't change anything. If I multiply anything by 1, it doesn't change anything. 200 times 1 is 200, right? So in that case, I'm not losing anything as a utility. What that means to me is if I take that cosine of, I have a 0 degree lag You know, we talk about leading and lagging all the time out there in the field. There is no lead or lag here. You can see those two waves, when they cross that axis, they're right there at the same exact point, aren't they? So they're totally in line with one another. But what we do is we take the old V equals IR, you can see up above to upper right of it. We can take that same and apply it to vectors. So where we're talking about vectors is we're talking about in the bottom right-hand corner, for you and I, we don't carry oscilloscopes or O-scopes out there in the field, right? We carry a piece of equipment that shows us vectors. So when we carry that equipment out there and it shows us vectors, this is what it's doing. It's essentially representing that wave you see over there is being represented with that vector. Okay? So here you can see it's showing the power right here. Now this is in the case where it says you got sinusoidal waveform only. There's no harmonics. So let's just look at an example down here. It's saying for 120 volt service that's drawing 13 amps at unity power factor, how much power is being drawn? Remember, we got unity power factor. So that's only going to be 1. So that's not going to change anything off of just simply multiplying my voltage times my current. So let's take a look at that. That's exactly what happens. So my power equals the 120 volts, all right, times the 13 amps, times, now we got 1, so it doesn't change anything. So I've got 1,560 watts, okay? So just so we're sure on something, because I get asked this out in the field. You know, we were showing that wave out there, and we were showing them right there in sync with one another, right? Well, here's the thing. If you think about it, when we're taking this, we're taking these sine waves and we're converting them to those vectors that you and I use, what it is this amplitude from here to here is represented the same in a vector, okay? So what's so important to us is, we've talked about this before, the length of the vector is the amplitude. So the amplitude on the wave is the height from my axis up to here. Well, that equates directly to the length of my vector when I'm looking on my test kit. Okay, so this is the vector here. So you can see the vector for this would be this long. The vector for this one would obviously be shorter, right? Because this is an amplitude value. So the length of the vector is an amplitude. If this were 10 amps, then that would be 5 amps. Okay? Now, also you notice in that, I don't know if you saw in the picture and picked up on it, and we're going to see that in a second, there's going to be, if there's a shift involved, then it changes things. And here's what we got right here is a shift. So what I'm going to say is I've got this here, and now all of a sudden I've got a shift involved. And the shift between those two waves right there, these sine waves, that shift, and in the example in a minute we're going to show it's going to have an angle, so that it's going to actually have a cosine of an angle, and it'll have a power factor that will affect our ultimate value is. This right here is equal to, remember we've looked at it 100 times, the angle between my voltage, let's say this is A phase, this is my voltage on A and my current on A. This equates to this, okay? And what you do is, so they've taken it and made it a lot simpler for us, so that we don't have to use an O-scope and look at this. We can just look at the angle between my voltage and my current, and that angle is theta, the same angle. Without getting into too much trigonometry, in my pea brain, the way that I think about it, to keep it simple, is the function of the cosine says the bigger the angle, it produces a smaller number. If you take the cosine of a big angle, it produces a small number. The cosine of a very small angle produces a big number. A very, very, very small angle, as in 0, produces the biggest number we want, which is 1. We go from 0 to 1. 1's the best we can get. So the smallest angle that we can possibly get takes us down to a power factor of 1. But as we start increasing that angle, it gets worse and worse and worse, right? So that's the key, and we say that all the time. We like to see those bad boys right on top of one another. We don't like to see a big angle. And now we can look here and look at some numbers, and we can see it out. So now if I have, okay, let's test this out and vet it out. I've got 120 volt service, it's drawing 13 amps. Here we go again. But this time, I don't have unity power factor. I've got a 30-degree angle. So with that, the cosine of 30 degrees equals 0.866. So what happens now, I don't multiply by 1. I multiply by 0.866. Clearly, that's less than 1, okay? And if I multiply by less than 1, I'm going to end up with less than what I would get if I multiplied by 1, and it proves itself out here. Now, I don't get that 1580 or 1560, whatever it was. Instead, now I've only got 1,351 watts, right? Because I multiplied by 0.866, which was lower, okay? Here's another example. Let's take the angle even bigger. Remember, bigger the angle, the worse the number. Well, let's prove it out right here. So for a 120 volt service, now it's drawing 13 amps, but now I've got 0.5 as the power factor. 60 degrees. Very bad. Well, so now if I do it, I only get 780 watts. Now you guys out there that are thinking about it, you're saying, oh yes, so that must make sense. Why do we use that 0.5 on the phantom load test? Because it's bad. Look how bad we end up. Now we're only at 780 watts coming from 1560. We're at half, okay? So that tells me if I can test that meter, and this is a little sidebar, is if we can test that meter at a horrible power factor, then we know that the meter should be good to go. So that's why we use such a bad one on that power factor test. Remember, we do a full load, we do a power factor, and a light load test, and we use that 0.5 on that. So in the previous example, as it says right here, our power was the 120 times the 120 volts, 13 amps, 0.866. We end up with 1,351 watts. But remember, you've seen your bills at the house. It's kilowatt hours, right? So it's kilowatts. So we need to talk about kilowatts. Well, that's just the metric system of saying if I've got 1,351 watts, if I divide by 1,000, then that gives me kilowatts, okay? So in this case, for 120 volt service, drawing 13 amps at 0.866 power factor. Remember that horrible 60-degree angle. So now we have how many kilowatts? So we say, okay, it's the 120 times the 13 times the 0.866, all the same. But when I divide by 1,000, I get 1.351 kilowatts. So I have 1,351 watts equates to just 1.351 kilowatts, okay? Which is how we get paid. Now, let's talk about the difference between energy and power. Okay, the difference between energy and power is, here in Tennessee, okay, you get paid by your energy, but we acquire power from our dams and from TVA around here, okay? So we get our power from TVA, but we bill the customers a bill on energy, okay? Because time is involved now. I kind of mentioned it before and hinted a little bit. It's kilowatt hours is what's on your bill, right? Not just kilowatts. There's the time component in there. And that's what we get billed on. That's what we bill our customers on also. So you can see here, I like this analogy. It says if power is how fast water flows from a pipe, and it is, then energy is how much water we have in a bucket after the water has been flowing for a specified time. So you can see here, if, for instance, if I let something run for a day, then it's gone for 24 hours. So now I have to multiply that to get my kilowatt hours. What's the bill? Well, you used that power for you used it for 24 hours, so I'm going to bill you for 24 hours of use. Okay? So you can look right here and see you've got the kilowatt hour for 1 hour is 1 kilowatt hour. So the time is always involved in it, like I said before. But here now we're going to actually put it in the units that we see, which is kilowatt hours. So when we do that, the time is involved, the energy is involved. So now you can see here we've got, versus just watt hours of energy, now we've got kilowatt hours because I divide by the 1,000 to get to where I need to be. Just like we did before on that conversion with the 1,000. Okay? Now here, energy, what we sell, just like we were talking about before. Well, here's two different examples. One's more of a commercial example, and here's one more of a residential example. And so what we're going to do is let's show you more of a commercial example right here. So I've got 120 volt service, because that's what we normally see out there at the meters, right, guys? Ladies, also, sorry. And so we see out there at the poles and stuff, we're most of the time dealing with 120 volt on all these transformer rated services. So we've got a 120 volt service drawing 45 amps at a power factor of 0.9 for 1 day. So how much energy, this is the billing number that we're looking for, has been used. So the energy is the 120 volts times the 45 amps times the 0.9 power factor, right? divided by 1,000. So then at that point in the parentheses there, we've got our kilowatts, right? But now we need to add that hours and that time component to it. So it says up there 1 day, that's 24 hours. So when I multiply by the 24, now it bumps it up to 116.64 kilowatt hours. And that's how we bill people, right? When that meter spin, it used to spin a lot faster and that pulses faster. When it used to spin a lot faster, obviously you're using more energy, right? Because you're spinning it faster for that amount of time, okay? So now for a 240 volt service, which is this is more residential, for a 240 volt service drawing 60 amps at a power factor of 1 for 5.5 hours, how much energy or kilowatt hours has been used? Well, you would just take the 240 volts and you would multiply it by the 60 amps, right? And then as soon as Chris will hit the button, you guys will be able to see it. So you take the 240 volts times the 60 amps, then times, in this case, it is unity power factor. You only multiply them by 1, but we have to divide by the 1,000 to get the kilowatts. But then this time, the time of the usage was only 5.5 hours, so we multiply by 5.5, and we ended up with 79.2 kilowatt hours. So now let's talk a little bit about, we mentioned, you've heard us, we're talking about this VA and power, and so let's talk about that. So the power is measured in watts, so the power does useful work, okay? The power that does useful work is referred to as active power. So that's in watts, but now I have VA, and VA is measured as just the voltage times the current. So it is the capacity required to deliver the power, okay? So it's referred to as apparent power. And the power factor is just, if you think about it, and it's going to become a little bit more clear in a minute because we're going to get to the power triangle, you're going to see that the power factor equals active power over apparent power, okay? So if you look at it like this, you got watts and you've got the VA. The way that I look at it as apparent power, if you think about it, that transformer sitting out on that pole is so many kVA, right? So I've got my power is sitting out there. It's the old water tank sitting there full, and the water tank's just waiting to do work until you open a spigot, and then the water starts flowing, and that's when the customer starts turning everything on, and now that transformer is supplying that power there, right? So that's the difference. I've got and then watts is what is used by the customer inside there. Of course, we use our calculations to get to kilowatt hours eventually to bill them on. That's the difference there between that active power and apparent power. So this is a great screen to show what we're talking about. If you've got as this power factor increases, it goes from 0.5 to 0.866, which is designating a 30 and then a 60-degree angle, and then unity, which is 0. And so you've got 1 there. What happens is the watts and the VA stays the same. You know, what I'm getting from TVA up here, you know, I'm paying for 1,560 VA out there. But actually, once we start getting down to the customer level, it gets down into the watts, which, once again, we know kilowatt hours. We'll make that conversion over the usage of time and do our math. But that's the difference of, I've got the generation folks out there that are always supplying me the same amount. Okay, what's available there is not going to change. But once it gets to the customer, that's when it starts getting a little bit more complicated, okay? So for a 120 volt service, drawing 13 amps at 0.5 power factor, 60 degrees, so how much power is being drawn? Well, we've worked this out before, right? The power would be the 120 volts times the 13 amps times the 0.5 power factor from a 60-degree angle, cosine of 60, we end up with 780 watts, okay? Now, how many VA are being drawn? The VA is just purely the voltage times the current. It doesn't take those angles into effect, right? The angles and all that occurs is once it hits the customer and we start dealing with the customer and the different losses, inductive motors, you've heard me talk about that before, that affects the power factor. All of that is what affects and creates why we have to use the other means to be able to calculate it, because there's no angles involved when we're talking about this VA right here. So it says how many VA are being drawn. It's purely just voltage times current. I end up with 1560. But when I add in that 0.5 power factor, look at that, it's half of it. And that's why we talk about, And I'm not trying to get advanced or anything, but you know, that's why we just talk about how it's so important to do the testing the right way, because you need to be able to take into account these power factors, okay? Because that's what kills us out there, okay? So now we've got a 120 volt service drawing 13 amps at 30 degree, okay? So now this is just a 30 degree angle, okay? So now we're at 0.866 for our power factor, so how much power is being drawn now? So it's going up some. Before we got nailed, it was 0.5, so now it's 0.866. So we're up a little bit. Now we're up to 1,351 watts. And can anyone guess what the VA is going to be? I'm sure everybody on the chat room is saying something. It's going to be the same thing, right? The VA doesn't change. The angles and all the complicated stuff that happens once it gets to the customer is not involved when we're talking about VA, okay? So we got the 120 times the 13 is 1,560 again, but this time there's a little change in the amount for the power because the angle was different, okay? So we ended up with only 1,351 watts. So now for 120 volt service, 13 amps for a 1 power factor and 0 degrees, how much power is being drawn? So the power factor is 120 times 13 times 1 is 1,560. So you notice that unity power factor, it looks like VA, right? Because we end up with the same amount because it doesn't change anything, all right? Because you're going to see how many VA are being drawn. 1,560. So it's funny, at unity, it almost acts like it looks like VA, right? Because it doesn't change the amount, but we know we never see unity in the field. So there's always, that's never going to work out in the field. You'll never see that in the field. I've never seen it. If you have, let me know. But there's always going to be some losses out there, okay? So in the cases where we have any kind of a power factor, any angle involved, you know it's going to be less than unity, okay? Okay, so now we get to bring VARs into it. Those nasty VARs. So we got watts, which is the useful power that does real work at the load, okay? So it can light a bulb, turn a motor. Then we've got VA that we just talked about, which is the total power in the system. Well, it is actually the vector sum of watts and VARs. So now these VARs, it's non-useful power, and it's required to drive the inductance or capacitance of a power line. So what does that mean? Well, if you go to the next one, you'll see here, VARs, you know, Southern Baptists, we're going to call that root beer. Some people use beer. We're going to use root beer here. So, so you got VARs equal foam, right, the non-useful stuff. The watts are the liquid, this is the useful, and the total, which is VARs plus watts, the total is the VA, which is the total power, okay? But we know, yeah, you can supply the total power, but we know there's going to be losses on the inside with that customer, so we're not going to get it all back. So there has to be losses, and one of them is with these VARs, okay? So lock that bad boy down. All right. Okay, so now that we've mentioned VARs, we got VARs over here, we've got watts down here, and we got our VA up here. And here's that theta, right, that we've talked about. So here's the relationship, and you've heard people mention the power triangle before. We don't have to get all crazy about this. We can keep it simple because this is basic meter math. So here's what we're going to say. We're going to say, you can see I've got VARs over here, I've got my watts here, and this is my total. And if you want to look at this, these would actually be vectors. They're adding this as vector math. Don't need to get all into that. We're going to keep it real simple. We're just going to say, if you look at this, we said the cosine of theta equals power factor, right? So the cosine of theta equals my power factor, which equals, you can see, and I'll just tell you, the function of cosine in trigonometry is on a triangle, it's the adjacent side over the hypotenuse, okay, is what cosine equals. And in a right triangle like this, where the angle is 90 degrees, they call this the hypotenuse, and then this would be, for this angle here, this is the adjacent side, and of course this is the opposite side of that angle. So in this case, it is the adjacent, which is watts, over the hypotenuse, the long one, which is VA. So actually, my cosine of theta, which is to you and me, the term we always hear, power factor, is actually equal to my watts over my VA. Or we said this is the total sum of the power, right, versus this useful power right here. So it's my useful power over my total power equals my cosine of theta or my power factor. So what it's done is it's taken to come up with my power factor using the triangle. I'm saying my power factor equals the useful stuff over the total. Okay? So where do VARs come from? I like Steve Hudson's slide here. Steve came up with this. It's showing the dam. We're Tennessee, TVA, lots of dams. So it's saying here you've got the inductance in the power transmission line, power factor, it increases transmission line, lower power factor, it increases VARs. So think about this, all the way from the dam, transmitting from the dam, all the way to a substation, from a substation all the way to your house, those long, long runs of those conductors increase the VARs. And remember, so you're increasing the foam in the mug. So you're taking away from the useful power and you're adding in the non-useful. It's just what you have to live with those length of conductors with your inductance and capacitance. So it's a built-in problem that we've got are these VARs when we're trying to transmit power and energy all the way from, power all the way from a dam all the way to your house, okay? So now we've added another column to our chart, and this explains where that went. You know, before we didn't have the VAR column. We just saw 1560, 1560, 1560, which was great for VA, but then all of a sudden, which is my total power, and all of a sudden, where did the losses go? Now you see where they went. They're in the VARs. So when I put in a 30-degree angle and at 0.866, I come up with, like we calculated a minute ago, I got the 1,351 watts. The 780 watts I'm missing are my VARs right here. And then when I go to a really bad one, when I have a 60-degree angle, you know, between my vectors there, now I've got a power factor of 0.5. So I've got only 780 watts and my VARs are 1,351. So you can see how bad that is. It makes sense that ANSI says, run that one on that phantom load test, and if it can make it through that, it should be fine. So they picked a really bad one. So you can see here, my VA does not change. What's available out there doesn't change, right, out on the lines. But what does change for me is I'm adding VARs in, okay? And when I add the VARs in, I'm adding the foam into the mug, so to speak, and I'm taking away the useful stuff because my total is going to stay the same, and it's the sum. So as the one decreases, the other one's going to increase. So as my VARs increase, here we go, inversely proportional again, right? My VARs and my watts. So because the 1560 is saying the same, but as my VARs go up, my watts come down, okay? Instrument transformers, CTs and PTs, right? You and I deal with those out there in the field all the time. So essentially what they do is they step down the voltage and current from these higher levels we have up there, these transmission, distribution, amplitudes, and levels up there, and they bring it down to instrument levels, which is appropriate for the metering. It's a lot, a lot safer for you and I. It affects the type of equipment you have to have at the bottom of the pole, because since I've stepped everything down, I can step down both my voltage and my current coming down there. Remember what we said power was, voltage times current. So essentially, I've got less power at the bottom of that pole now. If I transform that stuff down, I'm dropping my voltage and I'm dropping my current. And when I do that, I have less power available, which makes it safer to work at the bottom of that pole, right? And then, so we're also going to show you, we're going to talk a little bit about how do you determine the ratio on CTs and PTs, because once we know that, those ratios directly affect how you calculate your billing multipliers. Ding, ding, there's another big one for us, right? Billing multipliers. We say that's one of the biggest losses that we have at utility companies is off of billing multiplier errors. So let's talk about the instrument CTs for a second and talk about that math just for a second, okay? I'm going to go back to the board. Okay, so let's say we have an 800 to 5 CT. We have a 400 to 5 CTs. We're going to say these are CTs. Okay, so what does that really mean? What that means is that CT with a nameplate ratio of 800 to 5, it is saying you can think of this as primary current and secondary current. Primary current, secondary current. So that means fully loaded, which this would be fully loaded. Of course, rating factors, I understand all that. I'm saying just keep this simple. At 800 to 5, if I actually ran 800 amps through that CT on the primary side, so if I've got my donut CT out there and I'm running my conductor through there, if I run 800 primary amps through there off of my secondary terminals for that CT, for an 800 to 5 CT, I would have 5 amps over here. Okay? So 800 on the primary gives me 5 on the secondary. On a 400 to 5, one that's labeled 400 on the side of it, it means that if I run 400 amps primary through that CT, my secondary terminals are going to, off of this, if you read that, you would come up with 5 amps over here as well. Okay? So what change, what does that really mean when you start changing these numbers up? Oh, that's 800, I get 5. Well, what happens when I only have 2.5 amps on my secondary side? Well, then that would mean the ratio stays the same. Okay? So in this case right here, if it's a 400 to 5, if I have half, if I only had 2.5 amps over here on my secondary side, if that's what I read, then I know because it's a 400 to 5, that's half of that, then I take half of the 400, then I know I have 200 amps on my primary side, right? So it's in that ratio does not change. If that CT is working correctly, it does not change. So then that means if I have 400 on the primary, I have 5 on the secondary. If I have 200 on the primary, I have half of that because it's half of what I had here. And it works that same way. If it's a fourth of it, if I had 100 here, if I only had 100 amps here, I'd have 1.25 amps over here, which is a fourth of 5, right? So the ratio stays the same. It's 400 to 5, it's 800 to 5 here. If I only run 400 amps of primary on an 800 to 5 CT, I'll only end up with 2.5 amps on the secondary side. The ratio stays the same if it's working correctly. So now how does that affect us when we're talking about the billing multipliers? Okay, here's how it affects us when we're talking about the billing multipliers. I walk up to the pole and I look up there and I've got 400 to 5 CTs up there. Now I also have 2 to 1 PTs up there. Once again, the PTs work just like the CTs, and that's the ratio. It's always going to be 2 to 1. Okay? It's 2 to 1. So it's always going to take half of it, right, on the PTs. So if I have 480 on the primary, what will I have on the secondary? If I have 480 volts on the primary, what will be my secondary? It's going to be half of that, right? It'll be 240. So that's the ratio. It's 2 to 1. So it's always going to take half. If you think about it, the reason why we're doing all this step down of these transformers is think about the type of equipment you would have to have at the bottom of that pole to handle that much power. You'd have to have blades that thick on all this. The test switches would be monstrous. There's another reason why it's done the way it is, because if we step all this down, if we have less power available at the bottom of the pole, we can downsize all of the equipment down there. We can downsize the size of the meter. The meter only needs to handle 20 amps and not 1,000 amps, okay? And we all know that a meter that's able to handle 20 amps versus a meter that needs to be able to handle 1,000 amps, it'd be a monster, okay? And all those switches would be monstrous. So not only is it safer for you and I down there for less power available at the bottom of the pole, but it helps with the type of equipment and the setup we can have at the bottom of the pole for you and I to test with. Can you imagine how big the duct bills would be to go in there if you had that much power at the end of the pole? Yeah, you'd back it up, boys. Beep, beep, beep. Okay, so in this case, let's look at this. So we've got our step-down transformers. We've got CT that's stepping down my current. I got a PT that's stepping down. Instead of voltage, we use potential, right? Just like when you're talking about potential on a battery, the potential's on. We use potential. Some people use VT for voltage transformer. You see on some of these packs and stuff out there now, VT packs. But right now, we always go CT and PT. So this is taking my current down, and this is taking my voltage down. So if I looked up at the pole and saw both of those, let's do a conversion on this one to make it simpler for us. If it's 400 to 5, I can divide 5 into 400 and I get 80, right? So really, I could say that's 80 to 1 on the current transformer. So now, having these ones on the end allows me to do this, okay? You go out there and you measure it with your test equipment, and when you take the measurements, remember, it's been stepped down. So is that what really you're going to bill on, is what you test? No. That's what the billing multipliers are for. You step it down so that you and I can do our work, take our measurements, and come up with our readings. But when you get ready to bill someone, you got to step it back up, so to speak. You got to crank the bill back up because we've stepped this down. That current that they're seeing has been transformed down by an 80 to 1 ratio. So when we get ready to bill somebody, the billing multiplier is going to be, you're going to take whatever you come out with, okay, whatever you come out with, and you're going to multiply it times 80 and then times 2. So really, you're going to multiply by 160 whatever you come up with. Now, here's where we have the problems. If it's supposed to be 160 and somehow this gets left off and you're only multiplying it by 2, we're only multiplying it by 80 because of a mistake out there, and we've said that before. That's one of the major mistakes out there is billing multipliers. What happens then, and think about the bill. Instead of the bill being multiplied by 160 to go up, or the amounts measured rather, go up 160, by 160 to get to the bill, you only do it by either 80 or 2. You're losing your shorts, right? Because now, instead of multiplying by 160, I multiply by 2, I'm missing out by a factor of 80. The reason why I want to talk about this for a second is, when we're out there, guys, we can do a quick check of the billing multipliers. We talk about that all the time, right? We talk about going out there and saying, open up the can. A lot of folks have it written in the can door. Or, you know, you can check it off of, you'll have a report you carry out there and you're tested. You can do a quick check now and you can look at it and go, okay, I got a 400 to 5 and I got 2 to 1 PTs. That billing multiplier should be 160. And if you look in there, it's either 80 or 2 or 40 or some other number, it's time to raise the red flag, isn't it? Say, I think we might have a problem out here at JPS Industries, okay? So that, and this happens all the time. So I wanted you to have an idea of where they come up with that so that you can do a check yourself when you're out there in the field. Just look up there, a little quick math, and you can say, wait a minute, it's supposed to be 160. Why is 40 written down there? Or why is 2 written down there? Or why is 80 written down there? Call back and say, what do you guys have in there for the billing multiplier? And if it's not 160, then something needs to be changed, right? Okay. So meter registration. So we're going to, the meter registration is just a measurement of the meter's accuracy under, actual conditions. We talk about that all the time. We test for it all the time. That's what we test, either shop or in the field. So we're going to compare the meter to a standard, but we're really going to talk about it a lot. We're going to talk about that a lot more on Thursday. Okay, but I just wanted to let you know. We covered some of these basic, the math, and we covered how it's applicable to you, and then the CTs and PTs. But we're going to cover a lot more on Thursday. We're going to talk about actually going out there and do a meter and site test and some of the things to look for, both inspections, what to look for, and to come up with the meter registration here. And we're going to go over a little bit of the math with the meter registration, but you're kind of loaded up here now. You know some of the things, and it's going to come up here on Thursday of how we come up with this stuff, okay? So make sure you tune in Thursday, and like I said, you'll see where we come up with meter registration, okay? If anybody, I guess this is just an overall, I guess I should have said this earlier in some of the other ones. If you guys have got any questions about anything, call in here, okay? Call in here and talk to us, get on the website, click on us. We've got, everybody knows Ray Gore. If you've called in here, tech support ACE, and he's even got some backups around here. Call in if you've got questions or problems, or if you've got a question about this, or you want to see anything. And like I said, take advantage of, we're starting to get more and more people now getting these classes. So get in here and see if you can get, you schedule a class if there's a particular thing you want to see, particular test on a particular meter. We're having people now send us in particular, it's oddball stuff just to their utility and say, well, I know you haven't seen this much before, John, but could we look at this? And that's no problem. If it's possible for us to set it up, we're going to do it, and we can set up a webinar for you, okay? So once again, we really appreciate you guys tuning in. If you want to tune in Thursday, please do so, and we're going to talk about the meter registration and get into just walking up there, and it's going to be more of a basic. I'm walking up to test a meter installation. What should I look for, and what should I make sure I prepare myself for? Both a little checking out the site, a little safety, looking around, but also getting into some of the basic meter testing. Okay, so that's going to be Thursday. Remember, next Tuesday's 4-quadrant metering, and then the following week from this Thursday is going to be the ANSI C12 update. I know that I know things are crazy right now. We're going through a lot of stuff. Heard somebody say the other day, and I have to say I thought it was kind of funny. He says, "Can you believe anything made in China has lasted this long?" And but it has, and I just, man, please, y'all be careful out there. Everybody be safe. Let's not get too crazy and too lax. Let's just try and keep things in mind, because it's not always us that's involved, right? It could be one of our loved ones that could be older, have some health problems, that could be more susceptible to this. So just everybody be careful out there. And as always, we appreciate y'all, all you folks that are members of the Powermetrix family, and all you folks out there that are in our industry. We just wish all y'all safe travels and make it home safe every day. All right? Thank y'all. God bless. See you Thursday.